in this case, what we're going to do is just introduce you to the idea of projectiles and our basic analytical tool, which is to reduce the motion of a projectile into basically one dimension of acceleration and one dimension of constant velocity. So if we look at this projectile first, I'm going to run this simulation in interactive physics. This is a ball, and it has initial horizontal velocity, no initial vertical velocity. And I have this block here, and this is frictionless. So there's not going to be any slowing down or speeding up of it, and it's also going at 3 meters per second. Everything else is anchored into place. So this would be kind of similar to if I was walking across a room, me being this square here, and I dropped a ball. And if you were standing off to the side or something like that, this is what you would see. Now, there's nothing too crazy about this. What's going on is that because the block is moving at the same speed as the ball ends up dropping and hitting the block because that forward motion is not impaired by the fact that it's falling, nor is it sped up. Now, one of the things that we can do is we can go ahead and change where we're viewing this from, because right now we have what appears to be a pretty complicated motion of the ball. So let's change our point of view to that of the square. So now this with the eye on it is what we're focused on, and we're going to watch everything from the perspective of the square. What that means is that the square isn't going to move. It's going to stay exactly where it is. And if I run that, you can see that from the square's perspective, the only motion that's involved is the downward motion of this circle. As far as the circle is concerned, obviously it sees the rest of the world coming towards it at 3 meters per second. But from its perspective, the circle is going just straight downwards. And this is our first hint that we can reduce the motion of a projectile into two independent components. The one component is the downward acceleration due to gravity. And there's no difference between the motion that this has right now and the motion of free fall, because it is essentially free fall. Its forward motion relative to this is 0. So we have a freely falling object. Now we can switch the view around a little bit more. If we see things from the circle's perspective, things get a little bit crazy, or maybe a lot crazy, and we don't really have much need to do that. But we can look at things from the rectangle's perspective. That's just going to be the same as the initial case, where we had the forward motion and the downward motion. And if we switch once again to that of the square, we only see the downward motion of the ball. And as I said, that's our hint that we can analyze this motion in terms of a forward motion and a downward motion independently of each other. Okay, in this interactive physics simulation, what I have is two balls, and this one is just going to drop straight down. And there's one actually behind this ball that's sort of locked into place that's projecting off to the side. And so I'll run that once, and hopefully you can see what's going on here. That ball is coming out, and then it lines up with this right there, comes out, lines up right there, comes out, lines up, and so on. That last one didn't quite line up, but you can see the pattern here. Now, one of the things that I also want you to bear in mind is the times that are passing. So, first of all, neither of these initially has an initial velocity downward. They're both starting with 0 initial velocity downward. This one starts with 0 velocity at the side, whereas the one behind this one starts off with an initial velocity to the side, but no initial downward motion. And so if we watch this again, what we'll see is that after, looks like 0.25 seconds, they have matched each other exactly in terms of downward motion. So moving off to the side doesn't affect the downward motion. And this has moved exactly one square over. If we continue to watch its motion, you can see that the vertical motion is accelerating, which is as much as we would expect, but it's keeping in line for both the projectile and the one that's falling straight down. And you can see that in another 0.25 seconds, the horizontal motion has progressed by exactly, once again, one block over. So the horizontal motion of the projectile is not being affected by the fact that it's moving downwards. It's moving over one block every single time. And we'll look at it, another one. So 0.75 seconds, another 0.25 seconds later. Once again, it's progressed a lot further vertically. It's moved almost 2 full blocks vertically now. After moving maybe a third of a block initially, it's now up to moving almost 2 blocks, 1.5 we'll say, 1.5 blocks in 0.25 seconds. But it's still continuing to move 1 block over. And the last one, it moves over 2 blocks, a little bit over 2 blocks down, but still, in another 0.25 seconds, it's moved only 1 block over. And what this shows us, once again, very firmly, is that there is no difference in the vertical motion of 2 objects as long as they're under the effects of free fall and given the same initial vertical velocity. If I gave this one an initial upwards velocity, things would be a little bit different. If I went up like that, now they're a little bit off kilter from each other, ever so slightly. Okay, but assuming the same initial vertical conditions for the objects, we experience no difference in their vertical positions or their vertical motions later on, no matter what either of the objects is doing horizontally. And the same is true for horizontal motion. If I add in another block here, actually let me just do it like this. If I add in another block, and I'll put it right here, lined up with it, and give it a velocity of, I think I gave them 2.5 meters per second. Oops. I'm not sure why I'm getting that error. 4. Meters per second. There we go. And you can see that horizontally they are matching each other step for step. And actually, I didn't really want this one to be falling, so I guess that doesn't really prove my point. Let me just maybe put it on a track here if I can. There we go. So I just added a track so that it's constrained to the horizontal direction. And you can see it's lining up step for step. So the vertical motion, the fact that this one is undergoing, I'll bring it out so you can see it, this one is undergoing vertical acceleration due to gravity, doesn't change the fact that it's moving horizontally at 4 meters per second. And so what this allows us to do is analyze it in terms of not this complicated curvy parabolic motion, which is really a parabola. So we have parabolic motion here. And this is really complicated. We don't have to analyze it like that. What we can do is we can analyze it in terms of the motion horizontally of an object that's moving just horizontally, and we can analyze it in terms of an object that's just moving vertically. So we can take this complicated motion and break it into 2 parts. Horizontal motion, which for us with projectiles will occur at constant speeds because there's an absence of other forces unless we include air resistance, which we won't. I will ignore that for now. And the vertical motion, we can analyze it in terms of vertical motion due to free fall of gravity. And that's about it. That's the gist of the entire unit. You already know all the parts. You already know position, velocity, acceleration. You know how to deal with accelerations, how to deal with changing velocities. So the key for this unit is to take that understanding of what's going on and split a complicated motion, a 2-dimensional motion, into one problem that's horizontal, that takes into account the horizontal motion, and one problem that takes into account the vertical motion problem. So basically everything that we do will be split into 2 separate but interrelated problems. And the only thing that's the same about the 2 directions is that little number in the upper left-hand corner, time, how much time has passed. That will be the link between these 2 motions.